Hey everyone! Thank you so much for watching Weaviate on YouTube. This video will explore a super exciting new study into Retrieval-Augmented Generation titled Lost in the Middle: How Language Models Use Long Context. Lost in the middle is used to describe this U-shaped curve where we're exploring the impact of search result quality on the language model's ability to reason across the search results that have been put into the input. So we ask a question like, what is ref-to-vec? What is the atomic number of oxygen? What are cross-encoder ranking models? And we take that query and then we hit our search engine, get search results, and then we pass the original question plus the search results to the language model. So this has been something that's just super popular in application builders, hackers, but there hasn't been too much experimental findings on just the nuances of how exactly you're going to append search results into the input like this. So this is a super exciting paper that has this interesting U-shaped finding that is asking this question of where is the relevant information. So if we return 20 documents, is the answer in the first document, the 5th, 10th, 20th, so on, and then also what is the impact of how many documents we're going to return to then pass to the language model? Say we give 5, 10, 20, so on. So this was a really fun paper to read. I hope you enjoy this paper summary video. Really exciting to see more research, more understanding of retrieval-augmented generation. So quickly before diving into the experiments, to give a quick background on retrieval-augmented generation, we have questions that we want to ask a language model like about our particular data, whether we have some kind of particular software we're building, like in the case of Weaviate and ref-to-vec, or whether it's your legal contract, your particular data to analyze, your emails, so on. So we want to, instead of having the language model just be able to answer questions about our data, we're going to retrieve from a search engine and then put the information into the input to then help the language model reason across it. So whereas it would say, what is ref-to-vec? And it says, hey, I have no idea what that is. If you then give it the context where you've retrieved this text chunk from the vector database and it says Weaviate 1.16 introduced the ref-to-vec module, blah, 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 and then it's able to reason about what ref-to-vec is. So this is broadly the setup where we're going to retrieve information to put into the input to help answer the question. So the key question the authors are exploring in this paper is, how does search quality impact generation? In this initial example, this is an example of the Oracle context, where we have just the perfect context for answering the question, what is ref-to-vec? It gives you the perfect definition of it. But in the real world, retrieval systems are a little messier than this. We can't guarantee that the first result is going to be, the perfect answer to the question. So the question is then like, how does that error then impact the generation level? So, say this particular information about ref-to-vec was the third search result and the first was I don't know, something about cross-encoders, the second was something about replication, or so on. And so what is the impact of the needed information not being at the first, but at the third, 10th, so on? And, as you saw lost in the middle, the more it gets to the middle, the less the search engine, the language model is able to reason across it. So then there are two key experimental controls to study this phenomenon. How many documents are retrieved in the input, and then where in the retrieved documents is the answer. So they're going to be, firstly, they're going to control this to show exactly the impact of it by using the natural questions dataset and more details that we'll get into. But the key finding being that when you have this Oracle type of thing where you have the perfect answer, it's right there, you have really high performance and way better than the closed book, just language model answering the question. And this is on pretty general questions. So, you'd imagine if it's reasoning about your emails or whatever, obviously the closed book would have no way of reasoning across your emails or whatever. So, if it's in the first position, we get massively successful result. But then if it's in the 5th or the 10th, in the case of the 10th, it actually performs worse than not having any retrieved context. So just a super interesting finding. Odd thing about retrieval-augmented generation, really emphasizes the value of good search quality. But let's get a little further into the experimental details before coming back into that. So let's dive a little further into the experimental setup. So as you can see here, you ask a question like, who got the first Nobel Prize in physics, and then you have the relevant document. So in this case, the correct answer is in the second position. So you see how you retrieve, 3 documents, answers in the second. So the first question is about how many are we going to be retrieving? So you see the difference between retrieving 3 compared to retrieving 5 in this case. And then the next question is controlling where the relevant information is going to be. And again, I think another detail about this paper that I really like is that they're controlling the experiment. They have the ground truth, and it's not about like just the messiness of real world data. Although we will see they did an experiment on that as well, which is really interesting. But they have the answer, and so they're going to be controlling where it is 1, 2, 3, 4, so on, and that's how we were able to study this. So here's the first interesting set of results. We have the impact of the number of documents and the position of the answer, exploring 6 different models: Anthropic Cloud with 100K context, GPT 3.5 Turbo, and then GPT 3.5 Turbo with 16K input lengths, the MPT 30 billion instruct model, and LongChat 13 billion parameters with 16,000 input lengths. So the most interesting thing is seeing the kind of lost in the middle thing. Probably in the middle, you see when you only have 10, you kind of see it with the 5, but the 20 really shows it well, as does the 30. So anyway, so you see this kind of concept of like, if the answer is the 10th document out of 20, you get way worse search results compared to if it's like 1 or 2, as you see towards the left. And I mean, it's amazing to see that if it's 1, like the impact of perfect search would be just massive for Retrieval-Augmented Generation. But yeah, I maybe pause this if you want to look through it a little further. For me, just kind of seeing the U shape and seeing it come from 10, 20, 30. So the next really interesting thing explored is the impact of the number of documents. So again, these are, GPT 3.5 Turbo with 16K input lengths, Cloud 1.3 with 100,000 input lengths. So, these are pretty long context window models. So, one question would be, can we just, give it a ton of search results? Because then, we recall at 30 becomes a lot easier than recall at 1, recall at 5. But what they're showing is that in the current state of the models, the more you give it, the lower the accuracy. And this is averaged across each of the positions. So, when you see this plot, this point for 10, that's the average of when the relevant document is 1, 2, 3, 4 across the entire question answering data set, 30, so you get the idea. So the 2 key takeaways from these experiments are model performance is highest when relevant information occurs at the beginning or, interestingly, end of its input context. You saw that U shape that comes back up at the end. I think that's kind of interesting that, like, as it's attending, if it's at the very end, it goes back up. But so that's just one of those kind of quirky things about these language models and deep learning. So then the second thing is model performance substantially decreases as input contexts grow longer. So, we're not going to kind of solve this problem by, in the current state, we're not going to solve this problem by just giving it more search results and then hoping that by, increasing the window, we get the relevant target that way, sort of. Also, in the context of the final results, I think it's really interesting to just look at this table of the closed book versus the oracle. The oracle being, the information is search result number 1. So this is the case where we've solved search and we get perfect search results. But you see this difference, like with the MPT 30 billion instruct going from 31.5% to 81.9, or Turbo 56.1 to 88.3, just a huge potential in kind of improving search, and then what that would mean for the improvement on this. And it's worth noting that this data set, natural questions, we'll get a little more into it in a second, but this is like general knowledge. If this was about, again, I maybe said it to death, but like your particular Discord chat or Slack or emails or whatever, then there's like no chance at all at the closed book. But you still could fine tune the language model on your information, and then I think you'd be in a similar kind of camp as this. So this kind of, I think even with fine-tuning it on your domain, you still would want this retrieval. And then, I mean, we'll see as these experiments continue to evolve, and it's also interesting. But just this table right here, you see the impact, answering these general questions, having the first search result is just an enormous improvement. So one other interesting detail with their experimental results found in the appendix are some experiments with GPT-4. So GPT-4 is, the pink one that's at the, performing better than all these other models, and you still even see that U-shaped curve with GPT-4. So I think the deal, I read a little bit about it in the appendix, is that they do, you see it in the title of the plot, is that they do 500 questions to sample. So I think it hasn't been as fully tested as the other models. Maybe details with the API access. I think GPT-4 is still kind of a newer thing at the time of recording this video. So, you still see the U-shaped curve even in like the most powerful I don't want to pick favorites, but I think I think GPT-4 is widely regarded as one of the world's most powerful language models at the time of this recording. So as mentioned earlier, the current results we've been looking at have been in a really controlled experiment where the authors have the ground truth answer and they're explicitly moving it, 1, 2, 3, 4. But now let's see what this looks like in a more realistic, uncontrolled retrieval-augmented generation setup. So the next experiment is going to be using the Natural Questions Open Dataset, which contains historical queries issued to the Google search engine and then human annotated answers extracted from Wikipedia. But in this case, instead of controlling the system by explicitly moving where the answer is, we're just going to look at what happens with the Contriever embeddings retrieval system. So Contriever is one of these dense embedding models. It's been fine-tuned on MS Marco, and so we're going to be retrieving with that model to then have the input. And so it's a little more uncontrolled in the sense that where the correct answer is could be like 8, 3, 7, like whatever the performance of the retrieval model is. So this is the result that we find from that. So I think it's important to firstly start with what this orange curve at the top is. This is the recall. So as you retrieve 50, it makes a ton of sense that like recall at 50 is really high. You've retrieved 50 documents. So recall is like, is the correct answer in one of the retrieved documents? Whereas at 5, it looks like it's a little under 70. So then what you're seeing underneath that is the performance of the models when these documents are then given as input. So you see that, from 5, 10, 20, the performance saturates. It doesn't continue to improve. And some of the models, see like this drop from 30 to 40 in the MPT and so on. So it's more messy because it's more uncontrolled, because you could have, examples where the input or where the answer just isn't in the context at all. So that's what kind of makes it different from the original experiments. Okay, so now that we've explored this U-shaped impact of where the relevant information is and how much information we give to the language model, the authors then want to explore key value retrieval to answer the question of to what extent can language models even retrieve from their input context. So what that means in this case is we're going to be giving it key value pairs of randomly generated UUIDs. So like if you're using Weaviate, you know that this is the ID that you give to each of your data objects. So you have this key value, and then so the task then becomes key, 9F4 A, and then to output. So you're trying to measure just how well it can copy what's in the input. So similarly to the documents retrieved in question answering, we can also vary where the key value pair is going to be in the list, like say it's the 6th key value pair, and then as well as how many key values there are. So, these are just showing kind of that difference between, you have a lot of them or you have a few of them, and then how you can control where the query is going to be and then where it is in the context. So here are the results of the key value experiment. So shown on the far left, we have again this U-shaped curve where when the key is in the 25th or 50th, it doesn't perform as well as when it's the first key or the last key the last key is a little funkier with this. And also interestingly though, we do see that some of the models are really good at this, whereas others not as much. So maybe this is another kind of test for which of these language models you're going to be using. But we see as we in effort of trying to break it, this model, the brown one, the GPT 3.5 Turbo 16,000, once we scale that up to 300 key value pairs, and then we put the key to be reasoning about in the 200th position, then we get to around 45, it looks like. So it seems to do a better job at this than the other task, which is pretty interesting. I think being able to just copy that. There's a lot of like learning to copy with LSTMs and recurrent network work that kind of these kind of experiments have been tested before. But anyway, so these are the results of, again, finding some U-shaped curve in this kind of experiment as well. To further investigate these details, the authors are also going to explore the impact of architecture, comparing decoder-only models with encoder-decoder, experiments with query-aware contextualization, and the effect of instruction tuning. So to start off with encoder-decoder versus decoder-only, in encoder-decoder transformers, you first encode all the input into a vector, and then you would put that vector into the decoder that then attends over that vector, encoded by the encoder. So it makes sense to hypothesize that when you're encoding everything into a vector, maybe it has the context of looking at the entire retrieved search results, and that way it's able to see that even if it's in the 10th position, as we've been seeing with this U-shaped curve, it can still attend over when it's decoding only. But so they're going to compare the FLAN T5 XXL model with the FLAN UL2. I'm not super familiar with these models. I played a little bit with the FLAN T5 series when we were looking at before the ChatGPT thing came out. We were exploring these kind of models pretty heavily. But so anyway, so the interesting thing here is they don't really find that this encoder decoder only thing impacts that too much. But Another really interesting nugget that I think is really interesting for prompt design is this query-aware contextualization. So when you're decoding only, the model only looks into, only looks at the past. It doesn't like attend to the future tokens. So if you're saying, please answer this question based on the context, and then you don't give it the question yet, then it's just kind of like forming this representation of what it's looking at without the question to actually like help kind of guide its reasoning through the search results. So they're showing that a pretty big improvement by just putting the question in the beginning of the decoder only models. So that way it can, look at what it's reasoning about as it's building up the representation. So I like this quote particularly with that key value experiment. GPT 3.5 Turbo with the 16K inputs with query-aware contextualization achieves perfect performance when evaluated with 300 key value pairs. In contrast, without it, it achieves the lowest performance of 45.6%. So the difference between, what is the value of the key and then that key, like 9F4AB2, if you remember that, the difference between giving that before you then show the key values compared to you see the key values and then you ask this question, like that kind of thing. So I think that's pretty interesting for the prompt design for retrieval-augmented generation. So the next thing is this really interesting thing of trying to highlight maybe the bias of instruction tuning. So, thinking that with instruction tuning that, maybe it's biased towards the answer being right there because that's kind of how the instruction tuning might look like. So they compare the MPT 30 billion, the language model with the instruction fine-tune checkpoint. So I think there's a lot of confounding here because the language model is, not as tuned as the instruction models generally are, and that's why I think you see the accuracy is so much lower with just the pure language model. But I think what is really interesting is you're seeing the impact of Mosaic ML open sourcing the language model as well as the instruction tune. This is one such experiment. I think there are so many experiments that we can do by exploring the different fine-tuning routes from that MPT 30 billion base model. So I didn't really take anything away personally from this, but I love seeing this kind of like MPT 30 billion versus the instruction checkpoint and how that's been open sourced. I think that's all super interesting. So finally, one last thing the authors present is the serial position effect. The U-shaped curve we observe in this work has a connection in psychology known as the serial position effect that states that in free association recall of elements from a list, humans tend to best remember the first and last elements of the list. So, maybe there's something to that, comparing how language models recall things as well as how humans do. So to conclude, here are some of my reflections from reading this paper, Lost in the Middle, How Language Models Use Long Context. The first of which is the importance of search. So kind of, before the branding of vector databases, this was referred as a vector search engines or vector search databases. This kind of looking into information retrieval literature, following along with what search practitioners are doing, and the practices behind search has always been core to Weaviate. And just as an example, Weaviate 120, the latest release at the time of recording this podcast, video, introduces cross-encoder re-rankers, autocut, and new hybrid search rank fusion. Maybe you've seen like how you can combine BM25 with vector search in Weaviate. So search has always been first-class citizen in Weaviate, alongside that vector index and the database scaling and all that kind of stuff. So quickly, let me take you through these the three latest features just to show you a little further how Weaviate helps you get that better search that avoids that U-shape and hopefully gets you that Oracle context. So here we are in the Weaviate documentation to look at autocut, re-rankers, and new hybrid rank fusion. So I think autocut is probably the most interesting one for this paper. We've seen this other paper called Large Language Models Are Easily Distracted by Irrelevant Context, and that's all kind of motivated, even just human searchers want this kind of thing, where basically the idea is if we see a jump in vector distance, so we search something like what is ref to vec, and the first text chunk has the vector distance 0.1899, then 0.1901, 0.191, and then we have a jump 0.21. Autocut is a new feature in Weaviate that's going to look at these slopes and so cut it that way. So it interpolates a line between the vector distances. If you plot them on an axis of just x being where the search result is and then y being the distance, you interpolate that line, then you look for very steep slope changes in the distance, and so you'll cut that kind of thing. So when you're searching Weaviate, you have near text concepts, this animals and movies, that's what's turned into a vector. And then if you pass in autocut 1, that means the first steep jump detected, it will cut the search results. And this is a great way to only pass in the top 3 results to the language models, probably the best solution for this kind of the findings behind Lost in the Middle. So another interesting thing then is re-ranking search results. So we also have the re-ranker modules that were introduced in 1.20. So we have re-ranker cohere as well as re-ranker transformers. So re-ranker transformers is better for, say, local development. The Hugging Face sentence transformer libraries, they've open sourced cross-encoder models. Cross-encoder models, sorry, to set the stage a little more, they take as input the query and then each candidate document. So say you have five potential search results, it would take the query and then that first result, the query and that second result, and then output a higher capacity score. So you're trading off speed for a more accurate ranking. And as we've seen with Lost in the Middle, that more accurate ranking could end up being super impactful for retrieval-augmented generation. So with Weaviate 1.20, we have two ways of doing this. You can either use the local sentence transformers, or you can get an API key and use the cohere model. So cohere, they're offering cross-encoder ranking models as a service, as an API. So just really interesting stuff for the search quality. And so finally, with hybrid search, Weaviate has BM25 built in and vector search, so you can combine the scorings of documents with these two algorithms. And so when we first released this, we just had rank fusion, where you're just looking like it's ranked third in the BM25 and it's ranked second in vector search. So just combine it score it based on the ranks. Whereas now we have an actual score fusion. So score fusion, you're like looking at the particular score that came out of BM25, or similarly to AutoCut, you're looking at that like distance that came out of the vector search. So more ways of how we combine these results and overall deliver that, hopefully that Oracle search context. The second key takeaway for me is I want to see this testing other kinds of context. So right now what we saw is this setup where, K out of the N results are relevant. But I think in this whole, argument of how do large language models use long context, I've been just super inspired by the llama index idea, where you're retrieving from different indexes. So, in Weaviate, we separate data objects, kind of like categories of objects, into classes. So you have blog posts, podcast transcriptions, a code repository, or like Wikipedia. So I think the interesting thing in long context is to retrieve from each of these sources. So, again, I ask you, what is Ref2Vec? You might want to retrieve snippets from blog posts, Wikipedia entry, or like say a knowledge graph that has like, these tuples to give information about Ref2Vec, as well as podcast transcripts, like how is Ref2Vec used in conversation, and then maybe like code snippets of seeing it in action in some way. But this idea of retrieving from different sources, I think that's also a huge part of this conversation, and not just, only K out of the N results are relevant. But, of course, that's a huge part of it. And then you have the compounding effect of, as you retrieve from these other things, there could be irrelevant things as well. And that's why I think this whole re-rankers, AutoCut, hybrid rank fusion, it's also exciting of trying to, retrieve from all these sources and make sure that you get that, number one result is a good result. So then finally, I think a lot of these, we have these extractive question answering where what is the atomic number of oxygen? 8. And I think generally it'll be more interesting to explore the impact of, where the relevant information is, how much is retrieved in abstractive or, summarization, where you have to write these like long responses to bizarre questions that you can't just kind of like give a factual answer quickly to. So it makes the controlling of the experiment much more difficult, but, it's just kind of the evolution of this space. Evaluating generations broadly is quite difficult, but I think, just that is what I would predict is the evolution of these kind of experiments. Thank you so much for watching this video explanation of Lost in the Middle, how large language models use long context. I thought this was such an interesting paper, so cool to see these experimental findings on the impact of where the relevant information is in the retrieval-augmented generation setup, as well as how many documents are going to be then handed to the language model. I love seeing the key value retrieval, the exploration across different models, from the GPT models, the cloud models, MPT and long chat. It was overall just a really cool paper to read. So if you enjoy these paper summary videos, please subscribe to Weaviate on YouTube. It really helps, encourage us to keep making content like this. If you're curious about Weaviate, you can check it out on weaviate.io, open source on GitHub at weaviate/weaviate, and please follow us on Twitter at weaviate_io. Thank you so much for watching.